We have all witnessed this exact scenario. A hungry kid walks up to the pizza counter, jumps up, and asks, "Is it ready yet?" The cashier says no. 10 seconds later, the kid asks again. Every single time the kid asks, the cashier has to stop making pizzas, walk over to the oven, check the specific order, deliver the bad news, and try to get back to work. For decades, computers talked to each other in this exact same way. If an application needed new information from a server, it just kept asking over and over again until the data was finally ready. In software engineering, this constant asking loop is called polling. Polling is a communication technique where a client program repeatedly sends requests to a server at regular intervals to check if any new data is available. Every one of those empty checks forces both computers to burn processing power and memory. The asking computer wastes energy sending the request, and the answering computer wastes resources checking its database just to say, "not yet." If an event might happen in 2 seconds, or it might happen in 2 hours, asking every 5 seconds is a highly inefficient way to manage a system. To solve the pizza problem, restaurants introduced the glowing restaurant pager. You place your order, you sit down, and you do absolutely nothing until the restaurant actively alerts you that the food is done. On the internet, these digital pagers are called webhooks. Webhooks are automated HTTP messages triggered by specific events, allowing one system to push real-time data to another system without being asked. They flip the communication model from a demanding, "Are we there yet?" to a polite, "Don't call us, we'll call you." Let's look at how this pager concept works in the background of a normal online transaction, like buying a new video game. When you click purchase, the digital storefront is entirely dependent on your bank. The store has to wait for the credit card transaction to clear. Naturally, the store cannot hand over the expensive game files until they have concrete proof that the payment was successful. This animated diagram illustrates how the modern internet handles this wait. Instead of the store polling the bank simply sends a webhook directly to the store the exact millisecond the funds are secured. This digital signal packet contains all the necessary details of your purchase, and it travels across the network to the store's receiving server. As soon as that packet hits the store's system, it automatically unlocks the download button on your screen. There is no waiting for the next polling cycle. That instant notification from a webhook is the reason you can start downloading a massive digital purchase the very second you pay for it. To receive that signal, developers have to build a specific digital door, which is often done using Spring Boot. Spring Boot is an open-source, Java-based framework that provides developers with pre-configured tools to rapidly build and deploy standalone web applications and microservices. Spring Boot provides the underlying architecture that makes setting up these complex receiving doors incredibly simple. You just label the door, tell the bank where it is, and wait for the signal. For these digital doors to function reliably in the real world, developers have to follow 3 strict rules. The very first rule is asynchronous processing. Asynchronous processing is a programming model that allows a system to start a long-running task in the background while immediately returning to handle other incoming requests. Looking at this diagram, we see that when a message arrives, the Spring Boot application is polite and fast. It immediately sends a 200 OK signal back to the bank, essentially saying, "Got it." It is crucial that the application sends this confirmation before it actually begins the heavy lifting of updating the database, sending email receipts, and loading your game files. Because if the application tries to do all that heavy lifting while keeping the bank on the line, the bank's server will assume the delivery timed out, and it breaks the connection. Once the application successfully confirms receipt, it has to follow the second golden rule, the secret handshake. If a digital door is open to the internet, anyone can knock on it. That includes bad actors writing scripts to trigger fake payment approvals so they can steal free games. To prevent this, the real bank attaches a hidden secret code to the body of its digital message before it sends it. When the message arrives, Spring Boot checks this HMA signature to verify the sender's identity. An HMA signature, or hash-based message authentication code, is a cryptographic technique that uses a shared secret key to confirm that a message has not been tampered with and truly originated from the expected source. By confirming receipt instantly, the application keeps the connection alive. By verifying the cryptographic signature, it ensures the data is safe to use. This brings us to the final rule, shown in this diagram: idempotency, or no double eating. Idempotency is a property in computer science where performing an operation multiple times yields the exact same result as performing it just once. It ensures that if the bank accidentally sends the same payment notification twice, you don't receive 2 copies of the game or get charged twice. Which brings us back to the pizza counter. When the restaurant pager lights up, the wait is over and the food is ready. The next time you order delivery, book a flight, or buy a game, and your phone updates the exact second the transaction clears, you will know exactly what is happening. A Spring Boot webhook is quietly and efficiently buzzing in the background.